Let's get started. We got a full day ahead of us. I was talking about how Chapter 6 is like a whole job within itself. And I just did a quick search to see if there were any logistics jobs out there. And I found this one in Grand Blanc. Logistics specialists. Let's see, at logistics, XPO, or exceptional customer service is the heart of our success. As a logistics specialist, you'll play an important role in providing logistics and freight solutions for our global customers. Your strong work ethic, and attention to small details will ensure our operations continue to run smoothly. Join XPO will give you the tools and support you need to excel in your job and build a career. Pay, benefits, and more. We are eager to attract the best, so we offer competitive compensation with a generous benefits package, including full health insurance, medical, dental, vision, 401k, life insurance, disability, and more. And now here we go. What you'll do on a typical day, you'll perform 100+ inbound and outbound calls for loads to be picked up or delivered. Partner with the brokerage team. Now, the head of that brokerage team is the one who's most likely running the linear programming, getting everything scheduled for a whole bunch of weekly deliveries, and the team that you're on is the one making sure this all happens. You know, you should be expecting your delivery. You're trying to find other customers who need stuff to come back this direction so the truck doesn't come back empty. You know, it's hooking everything up. You have all these other people that are working with other companies, and if they have loads going a certain direction and you need to fill a truck because what you have on there right now is only 3/4 of the way, a partial empty truck is money out the window. That's how shipping, that's what we used to say at our company. We wanted a truck to be loaded from front to back before it heads out of the parking lot. That was a big deal. We partner with the brokerage team members to deliver exceptional customer service, communicate any issues, verify load details, and dispatch drivers. It's a good entry-level job right out of college to see how this really works in the real world. Chapter 6 is all about this one job. When we get to Chapter 9, it's all about a job managing projects. When we get to Chapter 11, it's about being a manager, managing waiting line systems, managing bank tellers that have waiting lines, managing big, large theaters that have waiting lines for 5 tickets. All of Chapter 11 is being that kind of a manager. Chapter 12 is all about simulation, which is a big part of your future, and you have to get your Chapter 12 simulation figured out because you have a huge simulation project coming up before you graduate. Anyway, I just wanted to give you an idea. What from this point on, every chapter is like, you find one that speaks to you, you say, maybe this would be a good entry-level job to get started in my career, if you like this stuff at all. And I know it's a minority as to who likes this, probably. Hey, wait, I can't let Chapter 4 go by. I drew a blank right here, if you recall, trying to figure out why this is being multiplied by 60. Overtime, the story said, there's only 50 hours available. It has to be less than 50 hours. And overtime up here for every 1 unit of OT is times $9, which is $9 an hour. So this is whatever number that, when it's figuring every possible solution, it's going to be in hours here. You have to multiply it by 60 to turn it into minutes. This is in minutes, this is in minutes, minutes. This can't be in hours. That's why it's being multiplied by 60. Sometimes the answer is so simple, and I don't know if you guys do this on a test sometimes, you think this is too easy, I must be missing something. And it happens to everyone, but I drew a complete blank for some reason. So, we got that figured out. Now, here's the second unit of this chapter. Let's talk about one, we'll do a quick refresher. What is this called, these circles? Nodes. Every node represents what in a linear programming? Constraint. What are these lines called? Arcs. Every arc represents what in linear programming? A variable. Okay. It's going to be the same for all 4 of these. You've got to get that down. These aren't going to be that hard. What you're looking at here, you're reading a problem. It's about stuff being shipped from somewhere to somewhere else. That's transportation, which is the one we learned already. But the story talks about stuff being shipped somewhere to somewhere else, then shipped on to somewhere else. That's transshipping. That's what you got to look for when you read these stories. That's really the thing I worry about the most, is you being able to tell which one to use as you're reading it. That, just like the inventory one. Remember, I gave some things to kind of pinpoint so you know whether to use this inventory or this inventory or this inventory. Same with these. So again, the story will read as if there is supply, there is demand, and for some reason there's things in the middle where goods go somewhere, then go somewhere else. This happens to be very, very common in the real world. Major retailers, for example, have things sometimes shipped to the main warehouses or manufacturers are making things right there, then go to distribution centers. They get broken down into smaller pieces, then go out to retailers. Walmart's pretty smart and kind of bypass a little bit of this by making deals with manufacturers to ship directly to the distribution centers and avoid the first step. So, that saves a ton of money on shipping costs. But a lot of companies will do it like this. In this example here, this is called Ryan Electronics. They manufacture, they produce electronic items in 2 locations, Atlanta and Denver. But because they're across the nation, they go to distribution centers with giant truckloads where there's other trucks waiting, break it down, mix it with other things that need to go to these retailers, fill that truck up, and it heads out to one of these retail locations. Sometimes it can even be a second distribution center, which then finally hits the retail locations. Now, you told me every node is a constraint. Do you remember on transportation, when it was on supply, what was the right-hand side of the constraint? Less than equal, greater than equal, or equal?
Less than.
Less than equal on transportation, when it's the supply, is the same rule for transshipment. So let me repeat it. Wherever the goods are coming from originally, the constraints are going to be less than equal. This is how many could be produced and shipped out, 400 and 600, but they don't have to. That's the capacity they could if it's all needed. And so we got to let the program say, hey, I know I can ship from Denver, but you can't ship more than 600 of them. I know I can ship from Atlanta, but not more than 400. That's our capacity for this time period we're talking about. Do you remember in transportation that the demands, which are usually like customers, the right-hand side of these constraints is less than equal, greater than equal, or equal. What was it? Equal. Equal. Always same rule for transshipment. The end location, where the stuff ends up at the end of this network, are equal sign constraints. Okay, now here's what's different. You have the distribution centers in the middle. And those 2 constraints, or 3, or however many middle nodes you have, are always equal to 0 constraints. Everybody hear that? This will have the right-hand side equal to 0. This will have the right-hand side equal to 0, because it represents whatever gets shipped there gets shipped back out. Nothing stays there. They're nothing but a distribution center to take big loads of things, split them up, and head out in smaller quantities mixed with other big loads to the different locations. So these are always equal to 0. These are equal to whatever the demand is. This is always less than equal to whatever the supply could be produced. So now those middle nodes. On transportation, all the arcs were positive numbers, or really just positive variables. And these arcs are positive. Notice the arrows are all going from left to right. This variable, this arc, is x24. And real quick, I almost forgot. Notice the nodes are all different numbers. We're not repeating 1, 2, 3 on this one, because this is where you'll. I think I mentioned Monday. If you started at 1 again here, start at 1 again there, x11, you don't know if it represents 1 to 1 here or 1 to 1 there. So on transshipment, you probably should always use different numbers on each node. So this arc right here is x24. And the numbers on top of these arcs are usually the cost for each unit to be shipped from here to wherever it's pointing towards. Or it could be a number of miles, and it's usually something representing that the company would like to have the least amount of, especially if it's cost, so they want it to be as little as possible. Every one of those numbers in transshipment, on those lines there, are only in the objective function, just like transportation. Everybody hear that? You're using the variables on all those constraints, but never use the cost numbers. Those cost numbers on each one of those lines are only in the objective function. That's the number one mistake I'm going to see on this quiz every semester. So I'm trying to emphasize it. If you're writing a constraint for this node right here, less than equal to 400, you're only using the variables of the arcs that are touching that node. I see 2 arcs touching it. So, so I'm doing Atlanta, and I see 2 arcs. X, what does it go with? 2, 3, plus X, 2, 4, less than equal to, and it can supply up to 400. There's the constraint for node 2. Notice I didn't put a 3 here, and I didn't put a, well, 1 is a 1, but I didn't put a 3 here because you don't want to have the cost in the constraints, only the objective function. How many variables will be in the objective function? You got it. How many?
12.
Yes, say it again. 12. All you got to do is count the arcs. That's how many variables in the objective function. Is this a min or a max? You remember what I just said a little earlier? Is this min or max? Because those probably represent costs of how much is shipped per unit. So I'm just going to start it for you. Min. Let's see. Up top we got x13 with a 2 in front of it. 2x13 plus. I see the second one down is I got a 3 on it going from 1 to 4. 3x14. Now you aren't going to make these little small numbers when you're typing it out, so it's going to look like 3x14. That's fine. I know that you're trying to tell me that this variable represents going from node 1 to node 4, and it has a cost for every unit being shipped on that path of $3 each unit.
And we only put the cost.
These are only in this objective function, both transportation and transshipment. The only difference is these middle nodes. So this company is doing electronics. They have facilities in Denver and Atlanta. Components are produced at either facility, may be shipped to either of the firm's regional warehouses, Kansas City and Louisville. From the regional warehouses, then, they supply the retail outlets in Detroit, Miami, Dallas, and New Orleans. So it's going from 2 locations, possibly to 2 locations, possibly to 4 locations. That story should click transshipment. I've got 3 columns of nodes instead of only 2. Now, who wants to volunteer to help me write Dallas constraint? Good. You're up. Ready? Let's do it. Let's do it. Dallas constraint number 7. Lee, tell me how many arcs are touching this node right here. How many arcs do you see touching it? 2. 2. Help them out on the right-hand side. Less than equal, greater than equal, or equal on Dallas. Help them out. Equal what? How much? 350. This is our customer. It has to be equal to 350. Now, lady, hey, don't interrupt me. Hey, what's on the left? Tell me what's on the left. Those 2 arcs you just mentioned are represented by variables where it's coming from and to. X, hit me.
400?
No.
And 600?
Help them. X. I hear it. 37. 37. Because one of those arcs you told me that are touching is coming from 3, and this is 7. Wait, give me the other one. X.
47.
47. That's it. There's 2 variables on the left because there's 2 arcs touching it. You got it. These are just like transportation. We have 2 variables, 2 variables, 2 variables, 2 variables. 2 variables, 2 variables. Now here's the difference. The middle nodes. I want to make sure everybody gets this. They're looking down already. I want to make sure everybody gets this. The middle nodes is the only hard part about this. How many arcs are, first of all, I'm going to put the right-hand side. I told you middle nodes always are what? That's right. Equal to 0. There's the right-hand side for a middle node. Equal to 0 on the middle node represents that whatever comes in, heads back out. Nothing stays. Comes in, heads out somewhere. But it doesn't stay. So, how many arcs are touching Kansas City node 3? How many arcs are touching it? I see 6 also. You see 6 touching it? 2 on the left, 4 on the right. Is that correct?
Yeah.
Okay, 6 arcs. Whatever comes in has to head back out. You have 2 coming in, so there's going to be 2 variables, and you have 4 heading out, which are another 4 variables, and you have to make one of those 2 sets negative and the other one positive, and it doesn't matter which way you do it, but the first one you do, if you made the ones coming in negative and the ones going out positive, you must be consistent with any middle node. So the bottom middle node would also have to have the ones coming in negative, the ones going out positive. Now, let me show you. Node 3, Kansas City has 2 coming in, X13 and X23. I'm making those negative. X13 minus X23, there's those 2 nodes. The ones leaving are X35, X36, X37, X38, and I'm going to make those are the opposite direction, so I'm going to make them positive. Plus X, I already forgot, 35 plus X36 plus X37 plus X38 equals, that's an 8, equals 0. That's the middle node constraint. That's it.
It's like the ones we did algebra on last year.
That's right.
So left side's always negative?
Left side always going to have a negative in the middle nodes because you have to either make the arcs coming in negative, or you got to make the ones going out negative, and you've got to have all middle nodes consistent, whichever direction you decide to do it. So now I'm going to do the second middle node at the bottom, but I got to look at what I just did to remember, did I make the ones coming in negative or did I make the ones going out? Because this is where you've got to be consistent. This is the whole, that will never work if you don't realize this, consistency. So help me out. What's the right-hand side on Louisville, the middle node Louisville? Equals 0. How many variables will be on the left on this middle node? No. How many variables? 6 variables. How many are negative? 2. The ones come in. What are they? Negative what? X 1, 4 minus X 2, 4. How many now positive variables are there going to be? 4. Let's see, I got to follow 4. It looks like 4, 5, 4, 6, 4, 7, 4, 8. Is that it? So plus X. I already forgot. 3, 5. Is that right?
4.
Ah.
4.
When you get old, it's gone. 4, 5 plus X 4, 6. I'm there now. X 4, 7 plus X 4, 8. There's a lot of electrical magnetic field coming around over here. So blowing the waves right through my head. 48. Everybody with me? These are too easy, aren't they? It seems like it, doesn't it? That's why you're going to study chapter 4. Once you realize how easy these are, you're going to focus on 4, because that's where I can see from your homework that you need to focus on reading a story and being able to identify those variables, come up with the objective function and the constraints. You guys got to practice. So if you remind me, I'll post more answers to problems from number 4 from the back of the book too.
We have to do that at the beginning of these too, though, don't we? If we're drawing this.
If you're either going to be given a drawing and asked to write the objective function constraints, or you're going to be given a story maybe and asked to make the drawing. As a matter of fact, in the story, if this were a quiz problem, you'd be given a chart just like this. So we'll say, hey, we make these electronic components in Denver and Atlanta, and we ship to our warehouses in Kansas City and Louisville. But from Kansas City and Louisville, we're shipping to 4 retailers: Detroit, Miami, Dallas, and New Orleans. And then you'll see these here. You'll say, and this represents the cost for each shipping route. And that's where the numbers on the arcs came from. This is what you haven't seen on the PowerPoint yet. It's a brand new PowerPoint, and I just noticed it's not putting in this part of the big picture here. But that's definitely something you need. That's how you're going to come up with the numbers if you have to make this yourself. For example, I'm on page 237, in case you have your book. Right here at the top, this problem saying, hey, we have shipments going from Cleveland, Bedford, and York to Boston, Chicago, St. Louis, and Lexington. This was Monday's example, by the way. And see all the numbers there. Those represent the cost per unit for Foster Generators transportation problem. And those are the costs that you're putting on top of each arc. If you draw an arc from Cleveland to Boston's node, you're putting a 3 on top of it. If you draw an arc from Cleveland to Chicago, you put a 2 on top of it. So everybody get what I'm... So when you have something like this, all these numbers on the lines, on the arcs, are coming from that little grid you have. I gotta make sure you're ready.
So,
You ready? I want to go one more thing. Hang on, sorry, Nathan. One more thing real quick. I'm pretending there's no number right there. Everybody see what I'm trying to do? You see this right here, you have the problem, but you don't see any number right there. Or maybe it's a zero, or a blank, or a dash. What does that mean? It means you cannot ship from Louisville to Miami. It's not an option. Do not draw an arc from Louisville to Miami. Leave it off. That's what this is telling you. If you have a blank or a zero there, that can't be done. You just leave that off, and when you write the constraint that had to do with Louisville and Miami, that variable, whatever that represents, will not be in that constraint because you didn't draw the arc. Because it's trying to tell you that's not, you're not, shipping to Louisville, Miami is not an option, is what it's trying to tell you. If that's blank or a dash.
if the table looks like this, it's gonna be what we did just now. with the
Transshipment, well, because you notice it's going from one location
Right.
to another location, then from those locations to another, that's a sure sign of
So
transshipment.
if it was just the bottom portion minus this top portion.
If it's just like, hang on, just like this you're saying, if it's just like this, where you
That's
only,
transportation.
that's transportation. Once we went from Cleveland, Denver, New York to Boston, Chicago, St. Louis, you don't see anything that's showing it going from Boston, Chicago, St. Louis, Lexington to somewhere else. That's transportation.
So are you gonna give us charts, or are you gonna?
Yeah, just like that. If I'm asking you to draw it, it would be just like that. But if I'm asking you to write the constraints, you're gonna get one of these. This is writing the linear programming model, and this one's saying draw the network. That's what you gotta be prepared for. And analyze the solution. Let's get back there. Again, wait, which one is this? Transshipment? Put this all together. We're going to use it. Here it is. Hey. Here it is. Here's all the variables for that transshipment one we just talked about. Look at these, less than equal, coming from those two places. Here's the zeros for the middle nodes. Here's the customer's demand. Look at the middle node. I have a negative and a negative for the two variables on the left. Positive, positive, positive for the four arcs going out of the middle to the customers. Same with that other middle node. Negative, negative, positive, positive, positive. Here's where my optimal solution is going to be placed. Here's where my objective function value is being calculated. Here's where all the calculations are placing the optimal solution in and multiplying it times its coefficients to get the left-hand side of each one. Are you ready? I'm going to ask you, anybody have the PowerPoint open? What is the route X35? 3 was the middle top warehouse. 5 was going to Detroit, I think. Someone got the PowerPoint?
Kansas City to Detroit.
Huh?
Kansas City to Detroit.
Is that what it is? Kansas City to Detroit is X35? So we're going to solve this. I want you to tell me how many are being shipped from Louisville. Yeah, Kansas City to Detroit is probably it. Set objective. That's going to be where the objective function value is being calculated. The optimal solution, D15, all the way over to O15. I have a whole bunch of less than equal to, 2 of them, and then the rest are all equal to constraints. Is that right? Are the rest of those equal to? Can't get it in the book. You sure are. So this is all set. I have the box check, simplex linear programming. I have the sensitivity this morning. How many are being shipped from Kansas City, node 3, to Detroit, node 5? 200. That's exactly like a question you might see on the quiz if a solution's up in front of you.
So what is the 2 above that? Is that how much it costs?
Well, this, yeah, the objective function, you're right, it is. So in this right here, this is going 550 times 2, 50 times 3, 0 times 3, 400 times 1, and adding these all together. So yes, that is 200 times 2.
So that's the number that will be on the arch.
That's right. That is, these are all the numbers on the arcs. Exactly. What does this represent, though? We were trying to minimize something on this transshipment. The numbers on the arcs represented, I think it was cost to ship 1 unit from somewhere to somewhere. So to get this whole, what do we have? A ton of units being shipped out to meet everyone's needs, if we add up the needs, I forgot. Are those in? 200, 150, 350, and 300, right? So there should be 650, 750, 8, 950. There should be 1,000 of them. Does that sound right? I just did the math too fast. And here we go. Is every customer getting their full order? Yes or no? For example, how many is Detroit getting? How many do they order, which is the right-hand side of the constraint, and how many are they getting, which is the left-hand side of the constraint? It would be, for node 5, would be Detroit, right? 1, 2, 3, 4, 5. Are they getting their whole order, yes or no?
Yes.
Right there. They wanted 200, they're getting 200. They wanted 150, they're getting 150. The other customer, 350, 350, 300, 300. Every customer, the end customer, is getting their full order. Exactly what they ordered. Okay. So, Nathan, I never got your question.
So the objective function value right there, that's the cost and optimal values.
Yeah, this is as low, if we have to ship all these out, I think it's 1,000, whatever. This is as low as we can get the cost for shipping. This is it, 5,200. There is possibly, as I said last time, another combination, but that could get us to 5,200 again, but there is no other combination that will get below this. So let's just go with this. You know, unless something comes up. 5,200 is as low as you can get the cost, and that's the objective. And before this existed, back in the old days, we were like trial and error. Well, okay, what if we do 500 this way and 200 this way? I mean, how much would that come to? Calculate real quick. Okay, what about this? This is so much easier. This gets you right to the optimal solution. The whole point of this is that the company's got to stop wasting money. If they stop wasting money, they have more profits, or they can even keep not having to keep their prices, retail prices, selling things going up because they're instead decreasing their costs. That's the whole point of all these chapters, to stop wasting money. I look around. You guys, anybody here wasting money? It's about 50% of our population is wasting money. It's just how it is. And that's how it is with companies. And they need people to go in there and say, hey, this is a better way. Let's use numbers to make this decision, and you'll stop wasting money. Here we go. You ready? This one's called the assignment. The assignment model. Let me get to this, and then we'll go back to the story. Here's the assignment model. In this particular example, how many constraints do you think there are? Anybody?
6.
Thank you. There's 6 nodes, 6 constraints, right? Now in this case, we numbered them 1, 2, 3 for Terry and Carl, Vic. And our client started at 1 and 1, 2, 3. That's fine because we don't have a third column. If I said X22, you know the first 2 is coming from here and the second 2 is coming from here. That represents that arc right there. How many variables are in this problem? 9 arcs. See them? 9 variables. If we were writing the objective function, we would be using all 9 of those variables with the number on the arc next to the variable. That would be our objective function. We haven't read the story to know if this is a minimize or max, but I can tell you from experience that assignment modules are used a lot at CPA firms when audits come up. They have all these accountants who can do audits, and they've got all these new orders for especially during tax season, for audits, and for them to assign project leaders to each audit, they'll go through an assignment thing to make sure they're optimizing something. Now, if it's a greedy law firm or a greedy CPA firm, they're trying to maximize the hours so they can bill the client as much as possible. And you hopefully will leave that company, but it happens every day. And if they're not greedy, they're minimizing the hours to keep their client's costs as low as possible. And that's really how this should be used. But from my experience, law firms especially do not look at it that way. They look at it the opposite. It's put a bad taste in my mouth. So nothing's changed. Here's what's changed. This story is going to talk about that there's only one of something that can be scheduled to each one of something, 1 to 1. So if this story is going on, it looks like we have project leaders here, and they have 3 clients who want something done, and one of them have to go to one of these, and here's, in the story, it's going to tell you something about these. This is their estimated completion time for the project clients, if that person's the project leader, based on their historical, what they've done in hours in the past. So this would be in days. If this person goes to this client, it's only 3 days. If this person goes to this client, it's 18 days. So now that we know it's days, it's scheduling project leaders to our client's project that we're going to see in the story here in a minute. Do you think this is a max or a min if this were an ethical company? Min those days, so our billing time is as low as possible, so this client wants to keep doing business with us, especially if they shop around. And they'll see we're trying to do the best for them. We're not going to gouge them. All right? Hang on, let me just stare at this a minute. Almost forgot. These are less than equal, just like transportation, transshipment. These are equal, just like transshipment and transportation. And let's write a constraint now that I just said that. We're going to do Terry's. Terry's constraint. How many arcs are touching Terry's constraint? No. How many? 3. What's the right-hand side for Terry? Less than equal to 1. There's 3, you said there's 3 arcs touching it. Follow the numbers. I got x11 plus x12 plus x13. Notice the first number, 111. The first number, I look at that and I know that's a supply node, because when the first number is the same, it means it's coming from one location, a supplier. Let's do client number 3. What's the right-hand side for client number 3? Equals 1. How many arcs are touching it? 3. Follow the arcs. x13 plus x23 plus x33 equals 1. Notice the number stays the same on the right-hand side where it's going to. This right away will tell me, oh, this is a constraint for a client or for demand on the right-hand side of the network, because the right-hand number stays the same. And if this were a detailed rating, for example, I'm real quick looking at whether you're making the right-hand number the same or the left-hand, because I know this should be a right-hand constraint, for example. That's a very common mistake, that you'll start changing the numbers that don't make sense. So you just follow the arcs and just write them just like the arcs are going. Okay, here's the story. Files management here we go. Let's consider files of market research, which has received requests for market research studies for 3 new clients. Company faces the task of assigning a project leader, or is an agent. These are called agent task network models. 3 project leaders to each of the clients. 3 individuals have no other commitments and are available to be the project leaders for these assignments. The time required to complete each study will depend on the experience and ability of the project leaders assigned. The 3 projects have approximately the same priority, and management wants to assign project leaders to minimize the total number of days required to complete all 3. Boy, there's a true ethical statement right there. Project leaders to be assigned to one client only. You'll get a grid that looks like this. Here's the project leaders. If Terry's assigned to project 1, 10 days, 2, 15, 3, 9. This is pretty small. Right now, I could say, everybody tell me what assignments you do to minimize days. And you would go, oh, look at 3. Look, there's a 3. Let's take Nick to client 3. We got let's see, we got 14 here. We can't take them again. Let's take the number 2, Carl, 1. That leaves us the best of the worst here. We got to go 15. 1 to 2. But usually you have 10 project leaders and 9 clients that need to get scheduled here. And so when you have more project leaders who do clients, one of them's not going to get scheduled. You're going to see that there's no assignment for one of them because you have more of them than you do those. And if you have more of these than you do here, just like transportation, and I won't put this on a quiz, you got to add some dummy project leaders. You can't have less project leaders than there are clients, so you got to add some dummies. However the dummies get scheduled when you do this, those are the clients who you have no project leader for, and you have to ask them to either wait or go find another firm. Right? Okay. the story goes, we have our 3 project leaders, here's what will take in days for our 3 clients. You're asked to draw this network. If you're ever asked to draw this network, the most common error is forgetting to put the 1s on the outside here and the 1s on the outside there. That's the most common error if you're asked to draw an assignment problem. You go back up here, you go, now I got my nodes in place, do I put arcs off of every one of them, go into every one of them? You look here, you go, look at this. Numbers, all of them have numbers, but if there were no number right here, this were a dash or a 0 or just blank, it's saying we cannot put this project leader on that assignment, so don't draw that arc. That's what it's saying to you. You draw it, it looks like this. We wrote our constraints. Our objective function would be minimize 10x11, 15 plus 15x12 plus 9x13. Right? Just like everything's been very consistent at this point, right? And now, here we go. There's our objective function, all of those variables. Here is the 3 project leaders, less than equal 1. They all have 3 arcs. Gave me one right over there. Just that one right there. Here's our 3 clients, equals, equals, equals. We did, which client did we do? Number 3, there it is, 1, 3, 2, 3, 3, 3, just like that. It looks like this on Excel. Did I do this one? Yeah, it looks like this on Excel. Do you see it? Let me minimize it. There. Too small? You see the whole thing? Just like every other problem. My optimal solution is going to show up here. Here's the costs. Here's the 3 less thans, the 3 equals to. Here's the left-hand side. Here's the right-hand side. We open up solver. I'm going to ask you a question. You got to answer it. I got to remember the names. Okay. Where is Terry going to be assigned? Here we go. Terry was number 1, right? Oh, it's not even filled in. D18, that was correct. This is a max? Just checking. There you go here. I'm going D15 all the way to L15. We got to put these constraints in. Oh, how could this not be done? We have 3 lessons in a row. So I'm going to go left-hand side with these 3. Go right-hand side with these 3. Let me add another constraint. It's going to be these 3. Now, grouping them together, start to say, I'm getting lost. Do 1 constraint at a time. I'm grouping them together just to save time because they're the same equality. We've got to switch this to simplex. And I said, where is Terry being assigned to which column? What? I used the wrong cell location. Boom. All right, let's do it again. Where's Terry being assigned? Which client? Wait a minute. Don't forget, every time you run that and you have another Excel spreadsheet open, it goes to the other one. There we go. Here's the assignment. Where is Terry being assigned? Client 2. Everybody see it? There should be only 3 1s there. The 1s are telling you the assignments. The rest are all zeros because that's not the assignments. Only 3 project leaders can be assigned to 3 projects, so you follow the 1s. The first project leader is going to the second client. The second project leader is going to the third client. The third project leader is going to the first client. That's it. There's only 3 jobs and 3 project leaders. And that's how you read this. Are there any project leaders? This is the project leaders. Are there any of them not being assigned to where over here would tell you if they're being assigned or not? They're all being assigned. And are there any clients not getting a project leader assigned to them? So, if you had a dummy one, though, there'd be another constraint for the dummy node, and that would have a 0 here. Because if that's the one that's not going to be scheduled. Or I'm sorry, the dummy will be assigned to one of these, but really it's being assigned to a client who can't get a project leader because we don't have a 4th project leader. Okay, we got 1 more of these. How are we doing on time?
Well, yeah.
Shortest route. This is the hardest one for a lot of people. It has some similarities to transportation, transshipment, and assignment, but there's a Shortest route has this little distinctive trick to it that makes it hard. I'm going to jump right to the network, and then we'll go to the story. Blah, 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 blah. Here we go. You ready? Shortest route is consistent with transportation transshipment, where every node is a constraint. That's the same. Every arc is a variable, but this has a twist. In shortest route, if there's no arrows on an arc, and it's between two middle nodes, not the beginning, not the end. Boy, I better say this again. It's not coming from the beginning, it's not going to the end, but it's between two middle nodes, and there's no arrows. That's a two-way arc, and it represents two variables, not one. Everybody hear that?
One more time.
Hang on. When you see the example over click. All right. Let me. Right here is the beginning, and every arc coming out of the beginning is a one-way, represents one variable. X12, X15, X13, X16, X14. This is the biggest node number, which represents the end of this network. And every arc touching it, going into it, is one variable. X56, X26, it's going this way, so where it's coming from too. X36, X16, X46. All of these middle lines that go between two middle nodes, here, 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 they're two-way streets. They're two ways, and they represent two variables. And a lot of people kind of forget that when, under the pressure of a quiz. And that's the hardest part about this. Every one of these middle nodes, because they have arcs coming in and arcs going out, the constraints are always equal to 0. I'm going to repeat that because that's a big part about shortest route. Every middle node, the constraints are equal to 0. That's the right-hand side of every middle node for shortest route. Go ahead.
So how do we know what's the middle and what's the end?
By the numbers. So the smallest number, the beginning always starts with a 1, and the end is whatever, count the nodes, is the largest number. If these 7 of them, be 7. If these were 8, be 8.
Okay, so 1.
1 and 6 are not equal to 0. 2, 3, 4, 5 are all equal to 0 for the right-hand side of those constraints. The beginning and the end of a shortest route, the right-hand sides are always equal to 1. The beginning is node 1. That is going to be equal to 1 for the right-hand side. The end is node 6. That's equal to 1. And all the other 4 are equal to 0. Now, here is how I hope this will kind of help you remember what to do with those middle nodes. It is just like transshipment middle nodes. You must make them equal to 0, and you have to make whatever arcs are going into a middle node either positive or negative, and whatever arcs are going out of the middle node has to be the opposite, positive or negative. And once you do your first middle node and you decide which direction is positive or negative, you must be consistent with every middle node. You with me on this? I'm going to stay consistent with how we did the transshipment, and I'm going to make my middle node, my middle nodes, every arc coming in, I'm going to make it a negative. Every arc going out, I'm going to make a positive. You see those letters? They're really going to be numbers. These are numbers. Right now they're letters because we didn't get that far, but they're numbers, and they represent either a cost or a profit or something you're going to minimize or maximize. So let me say this again. Just like transshipment, just like transportation, those numbers are only in the objective function. Let me say it again. None of these numbers are in the constraints. They're only in the objective function, just like transportation, just like transshipment, and just like assignment, now that I think about it, right? All of these 4, it's not the same. That is not the case with the 5th one, by the way, which we're not going to go over because it's not going to be on the quiz. But for these 4, that's the case. Those numbers are only in the objective function. So ignore those letters for now. When we talk about writing a constraint, let's look at constraint 2. See constraint 2. What's the right-hand side for constraint 2?
0.
What about 0?
Equal.
Thank you. Equals 0. There's the right-hand side.
Oh,
How many arcs are touching number 2?
is that, yeah.
That was just for the last problem. How many arcs are touching 2?
3.
3 arcs. How many of those 3 arcs are coming in, and how many are going out? By the way, let's get this right. There's more than 3 arcs. I'm sorry. I forgot. There's more than 3 arcs. You only see 3 arcs, but you forgot the rule. How many? 5. Not 6. 5. Because the one coming from the beginning is only a one-way. You cannot go back to the beginning. Anything coming from the beginning or going to the end are one ways. They're one variable. But all the other arcs in the between 2 middle nodes are 2 variables, 2 arcs. So, go offside. That is going to the end. This one is 2 variables. X, 2, 3, or 5. X, 5, 2. X, 2, 5, and X, 5, 2. Is that line at the top. This one is going to the end, which I didn't think it was. I thought it was going to the middle. That's a one-way. X, 2, 6. This one coming from the beginning is a one-way. That's X, 1, 2. So here we go. I said X, 1, 2 plus any order you want. Doesn't matter. X, 2, 6. And then we have a middle one. So this is going to be plus X, 2, 5 plus X, 5, 2. So 4. Get it? Wait, I'm sorry. What did I miss? Say it,
Is it
Dave.
supposed to be negative?
One, that's right. Which ones are coming in? Which variable's coming in? That's right. Now we've got it done. I'm making whatever's going in negative, whatever's going out positive. You know, and you look like you were sleeping, so I really, I think that was excellent. Thank you. No offense, man.
Oh, okay, then that's fine.
It was just a look.
What about the last one?
Right? You want to do the last one? What is it equal to?
What is X, isn't X 5 2 supposed to be negative?
No. Oh, is it going in? Oh, look at that. Oh,
Oh.
Late. You're
Okay.
fired. Oh. Oh. All right. Help me with node 6. What's the right-hand side of node 6? What node was this, by the way? This was node 2? Okay. Help me with node 6. What's the right-hand side? Equal 1. How many arcs are touching it? 5. And are any of them two-way? Because they're coming to the end. They're all one way. So they're all going to be positive because they're just one way. You don't distinguish negative and positive unless you have some coming in and some going out. If it's only going one way, they're positive. So I have x16 plus x26, how we do? Good. Plus x56 plus x36 plus x46 equals 1. This is node 6, right? I'm not going to do node 1, but it's just like node 6 because they're one ways. So it's going to be x12 x plus x15 plus x13 plus x16 plus x14 equals 1. I want to do another middle node. Make sure you take into consideration that we've already done a middle node and we're now thinking about it being consistent. Jump in.
Does it matter which way you write it?
Which way I write it?
Yeah.
No, these can be in any order.
Okay.
What matters is, though, that,
Design.
yeah, any order, though. Let's do node 3. This is node 3. Help me out with the right-hand side, Matt.
Zero.
Yeah, Matt's not, he doesn't even. Equals 0. All right? Equals 0. Are you ready? How many arcs are touching node 3? Give me a second. I don't even know. 6 it is. 6 it is. That's what I see. You guys see 6?
Yes.
You see it? Help me out. Let's start with going into 3. X. 1, 3. Negative. We've got to stay consistent. Whatever's going in, we did one already. We made the ones going into a node negative. We have to stay consistent. What else is going into 3? Minus X.
We didn't do it 4.
I can't hear you. 4, 3 is correct. Minus X. 5, 3. Plus X.
3 5.
3, 5. Plus 5. Plus X. 3, 4. Plus X.
Oh, 3-6.
3-6. There's 6 of them. 3 negative, 3 positive. We're staying consistent with the ones coming in being negative, the ones going out being positive. I've broken this down to make it as easy as I can for you. We haven't even gotten the story, and you can do everything that's necessary right now to take this quiz for this. I want to make sure you realize you do never have to draw a shortest route network in this class. But you do have to do the other networks. You have to be ready to draw transportation, transshipment, or assignment, but you do not have to draw this from the story. If this is a quiz problem, you'll be given a shortest route drawing already. You have to recognize the shortest route, but it doesn't seem that hard to tell the difference between this and the other ones, all right? So then you recognize the shortest route, you grab your note, middle arcs go 2 ways, it clicks. You've got to remember to make something negative and positive, and then you stay consistent, you're good to go. If this is a quiz question, I would probably say, write the constraint for node 5 and 3. I want to see you write those 2 constraints, and I'm looking for consistency because they're both middle nodes. Everybody feel pretty good about this? This is getting too easy, isn't it? What? It's the first chapter I understood. Honestly, thank you, Diane. Let's go to the story. The story is not even that important now. How are we doing? We're doing good. Susan has an important business meeting in Paducah this evening. She has a number of alternative routes she can travel from the company headquarters in Lewisburg to Paducah. Before I go on, these are the alternative ways she could go. She could take train, then take a plane, then take a bus, then a taxi, or a train, or a bus. Train, bus, taxi, I think those are all the options. And you can see the nodes. The route is the node. We're going to replace these letters, though, with cost. Here's the cost of each ticket that would be on that arc, but we're not just paying the ticket. We're not paying the cost of the plane ticket, or the taxi ride, or the bus fare.
Oh, so she don't care.
She gets paid during the transportation. How much she get paid? That's the rest of the story. The network of alternative routes and their respective travel times, ticket costs, transport mode appear on the next 2 slides. While Susan is being taken to this meeting, she's earning $15 an hour. It's an old slide. We'll take it to $20 an hour. Why is it minimized, Diane? Why?
That's what I'm saying.
I'm asking you.
I wouldn't want to minimize.
If you're doing this and you work for the company and I'm your manager and you're telling me you're not minimizing this because you want to make as much money as you can to make the ride long,
I'm not going to
I
tell
gotta
you
let
that.
you go. I don't know. I mean, come on.
I would either
Do I come
say-
across like somebody who gets these past me? Do I seem like that? Yeah, and when you're lost, you're on your time. Now we're adding the $15 an hour based on the amount of time each transportation will take. Some of these are an hour, so it's just the 15 plus the time. Oh, here's the time. Here's the ticket cost from the previous slide. These numbers, the total cost of each part of that route is what's going to go on each arc in place of those letters. And then it looks like this. Hey, what? Hey. Darn it. Yeah, I don't see it. Here it is. What we did, here's that equal to 1 from the first origin. Node 2 equal to 0, 3, 4, 5. I want to check 3, see if we got it right. Look at node 3 here. Negative x1, 3 plus 3, 4. That one, there's those 2. And then it says plus 3, 5, plus 3, 6. There's 3, 5, there's 3, 6. Then it says minus 4, 3, and minus 5, 3 right there. Those are the 6 ones. There they all are. We're going to put this, we're going to use Excel to solve it. This, by the way, would be the software output, what it would look like. If we're going to use Excel, you guys have to be Excel professionals when you leave the school of management. Your whole rest of your life is going to involve Excel, no matter what job you're heading towards. Marketing, human resources, supply chain management. You ready? Here we go. Look at all the variables. Ready? Here's left-hand side, 6 constraints. Here's all our total costs. If this were a quiz question, I'd say if we were to click on E18, what would be the entry we would see there using cell locations? Are you prepared for that quiz question?
No.
Yes.
I'm
I
kidding.
appreciate your honesty.
I'm kidding. You add them all together.
You realize it's that easy, right? So you're going to study chapter 4 for me, right? Here we go, solver. E18. It's a minimize. E through U. They're all equals to, so I lumped them all together in one simplex. I want you to look at the optimal solution because I'm asking you what is the route she's taking. You ready? What happened? Hang on, let me get here. Hang on.
Let's go back to the one.
What happened? Every time you solve, you have multiple Excel spreadsheets open. It jumps to a different spreadsheet. Let's talk about her route. Help me out. She's leaving. What was the name of the city she's coming? Louisville, Lewiston or something? And then, which is node 1, and then going where? 1 to what number?
3,
3. Then 3 to where?
4,
Follow the 1s. 4. Then 4 to where? Follow the 1s. 5. Then 5 to where?
6.
There's the end. There's the route. 1, 3, 4, 5, 6. 1 was taking some kind of form of transportation with her hourly wage is $40. Going to 4, whatever the form of transportation is $30 plus her money. $50 on this one, $30 on this one. The total cost to get her there is only $150. At the lowest we can get the cost. I just want to look at the form of transportation real quick. Let's see. Okay. Oh, hang on. What's the first one? 1 to 3? What letter is 1 to 3? C. So what is she taking? A bus for 2 hours to start with. Then it's going from 3 to what? 3 to 4, which is what letter? H. So then she's going to take a taxi for an hour. Well, there's no way it costs that. What would the taxi for? $40? There is no way. That's 5 minutes in a taxi.
Yeah, that's
And then 4 to 5 is an I. Form of transportation is a train for 2 1/3 hours. Wow. Making a lot of switches here. And then from 5 to 6 is L. And L is a train for another train for 1 1/3 hours. Yeah. This is a very busy schedule, but we're saving a ton of
Yeah,
money.
go look to see what B is.
That's what matters. That's what matters. And she's complaining it's taking her whole day to make all these switches, but we're paying her for it, so that's okay.
Look to see what B is.
B?
Yeah.
B is 1 to 5,
Oh.
which would be plain. $115 would be, so we know if you add that plus $15 to be on the plane, $130. Does that take her the whole route?
L, what's
No,
L?
you're thinking D. Right here, this whole
No,
thing,
I want
straight,
to do the
straight
plane.
shot. That is a plane.
No, the plane is B. Let's do
Oh,
it.
that's taking a taxi for 6 hours?
No, it would have
Oh.
been cheaper. It would have been cheaper to do 1 to 5 and 5 to 6. 115 plus $10.
But you got to look at this. Now, you got to take the hourly cost into consideration. Right. You got to do the whole thing. You ready for the class? We just finished chapter 6.